All right, so today we're going to do some practice with some circular motion problems to continue our unit on circular motion and uniform circular motion. So we're going to start with this problem here that says, what's the maximum speed a 1,250 kilogram car can drive if they want to go safely around a curve with a radius of 74 meters? It tells us here that the coefficient of friction between the road and the tires is 0.58. So if you want to go ahead and pause the video to get that problem written down, go ahead. We're going to start working through this here. So first of all, when it tells us maximum speed, that should tell you right there that the variable you're solving for is velocity, right? We're looking to find velocity here. What's the absolute fastest that we can travel in order to round this curve safely? Okay, when we're looking at a curve here and we want to find out what's the fastest we can go, that means we want our centripetal force to be equal to, but not greater than our frictional force. Okay, if our centripetal force was greater than our frictional force, that means our car would be going too fast and our car would begin to slide. Okay, we want our centripetal force here to be equal to or less than our frictional force. Okay, if our frictional force is larger than our centripetal force, that doesn't mean we'll stop moving, but it means it'll keep us on the circular path we want to go without having our car slip and slide off that curve. Okay, so setting these two equal to each other allows us to find the maximum speed we can travel without moving off of our path in any way. Okay, so once we've got this set up, we can kind of start doing our substitutions here. So let's look at what else our problem gives us. It gives us our mass. It gives us the coefficient of friction. And that's it, right? Oh, and the radius. I'm sorry, radius is 74 meters. All of those are in the right units. We don't need to do any conversions here. So we can start looking at our equations for centripetal force and frictional force. And I'm going to go ahead and substitute those two things for their individual equations. Okay, so centripetal force we know is equal to mass times v squared over r. And we know that the frictional force is equal to the coefficient of friction times the normal force. Okay, and right now we have mass, we have radius, we have the mass, we have the radius, we have the coefficient. We're solving for velocity, but we don't have the normal force yet. Okay, we're missing the normal force. So now we have to go back to our forces chapter and think about how we can solve for the normal force. So if we've got a car that's traveling in a horizontal path, is that car accelerating in the vertical direction at all? Okay, so if we look at our free body diagram, essentially of our centripetal force, frictional force, normal force, and gravitational force, since our car is not accelerating in the vertical direction, those two forces should be identical, right? Our normal force should equal our gravitational force since that car is not accelerating in the vertical direction. It's not moving up and down at all. So that means the normal force we're going to solve by taking the mass times 9.8. And that gives us a normal force equal to 12,250 newtons. Okay, so now we've got every component we need to solve our problem. All right, so algebraically, I'm going to go ahead and solve this problem by combining the whole right side of our equation. So 12,250 times 0.58 gives us 7105. Okay, which is going to leave us with 1250 times v squared over r equals 7105. Okay. From there, I'm going to go ahead and, we know our radius here of 74. From there, I'm going to go ahead and divide by 1250 on both sides. Divide by 1250. And that leaves us v squared over 74 equals 5.68. Now I'm going to multiply these two together, and then I'm going to square root that answer. So I get about 420, and when I square root that, that gives me a velocity of 20.5 meters per second. Okay, so that means the maximum speed I can go around this curve without slipping and sliding off of the curve is at a velocity of 20.5 meters per second. Again, the reason that we can set this equation equal to each other, this is how we get the whole thing started. Centripetal force is equal to our frictional force. When those two are equal, that means we are moving at our absolute fastest velocity, at our maximum velocity. We've reached a point where our centripetal force is equal to our frictional force, so we're doing just enough to stay on our circular path and to not slip out. Okay, we're doing just enough to keep that on track. So let's go ahead and try another problem here. All right, here's our next problem. It tells us the ball on the end of a string is whirled in a vertical circle with a radius of 0.45 meters. If the ball has a mass of 1.35 kilograms and the string can withstand 17 newtons of tension, what's the maximum speed the ball can be moving at the bottom of the arc? Okay, we're only looking here for the bottom of the arc. So what this is saying is that if we're whirling a ball in a vertical circle, that means we're standing here and our ball is moving in a circle like this. Okay, we're not looking at a horizontal pattern. We're looking at a vertical pattern. Okay, so our ball is swirling in a vertical circle. So let's go ahead and look at what this object would look like at the bottom of the arc. Okay, here's the bottom of our circular arc, and here's our object. Okay, we're at the very, very bottom of its circular path, and we've got tension here in our string. And the tension goes toward the center of the circle. But we've also got gravity acting here. Okay, this ball is not escaping gravitational force. It's not escaping that motion. It still has gravity acting on it. Okay, so now we're going to go ahead and look at our overall net force equation, or our centripetal force. Okay, here our centripetal force acts as our net force because it's our overall kind of force that's keeping us in this circular path. So we're going to set centripetal force equal to our upward forces minus our downward forces. Okay, again, our centripetal force here essentially acts like our net force equation, and we're taking upward forces minus downward forces. So it tells us in our problem that we can withstand 17 newtons of tension. Okay, that means F sub t we know is equal to 17. We know that F sub g is equal to mass times 9.8. So we can go ahead and take that mass of 1.35 times 9.8. And we get a mass of 13.23 is equal to our centripetal force. Okay, so I'm going to go ahead and do that subtraction, which means our centripetal force is equal to 3.77 newtons. However, that's not what we were asked for. We were asked for the maximum speed the ball can be moving at the bottom of the arc. So maximum speed here means we're solving for velocity. Right, we're looking at velocity. So now we're going to take our centripetal force equation, m times v squared over r equals 3.77. All right, our mass is 1.35. We're solving for v squared, and we know our radius is 0.45 meters. All right, so go ahead and solve that algebraically. So if you want to pause the video and solve that on your calculator, and we'll see if we match answers here in just a second. So here I get a maximum velocity, or a velocity equal to 1.12 meters per second. 1.12 meters per second. Okay, and the way that I went about solving that is I first divided by 1.35 on both sides. Okay, that way I've crossed that out. Then I'm going to multiply that whole thing by 0.45 times 0.45 on both sides. And then after that I square root the whole answer to get V by itself, and I get 1.12 meters per second. Something else that I want to do with this problem is I want to look at the maximum speed at the top of this particular arc. Okay, so I want to look at the same situation, but I want to look at the maximum speed it can be moving, or the speed it should be moving in order to keep in its circular path at the top of its motion. Okay, so I want to find out what's the maximum speed at the top of its arc it could be going through in order for the string not to break, in order for it to keep in its circular path, things like that. Okay, so let's find out what is the maximum speed at the top of its motion rather than at the bottom. Okay, and the way that this changes is that our free body diagram for this particular example changes. Okay, and the reason that it changes is because our tension force is pointing toward the center of the circle, because our string is obviously swirling from the center. And our gravitational force is also pointing toward the center of the circle, because it's still trying to pull it in the downward direction. So that changes the fact that we're going to be pointing essentially both of these objects toward the center of the circle. Anytime we're looking at uniform circular motion, we consider the center of the circle to be the positive direction. Okay, so although these are pointing in the downward direction, we consider the center of the circle to be positive and away from the center of the circle to be negative. So that means when we set up our net force or our centripetal force equation, we're going to take the force of tension plus the force of gravity, because they're both going toward the center of the circle. Okay, when we looked at the bottom of our arc, when we looked at the bottom, we had our tension going toward the center of the circle, which is positive, and we had gravity going away from the center of the circle, which was negative. And that's why we subtracted them, and in this case we're adding them together because they're both pointing toward the center of the circle, which is the positive direction. Okay, we know that our tension force is still 17. We know that our gravitational force is still 13.23. We solved for that last time. Okay, but this time we're going to add them together, which gives me a centripetal force of 30.23 newtons. From there I can go ahead and substitute m times v squared over r equals 30.23. My circle doesn't change radius. So I'm going to go ahead and solve now for velocity. So I'm going to take 30.23 divided by 1.35 times 0.45, and I'm going to square root that answer, which gives me a velocity of 3.17 meters per second. Okay, so at the top of its arc, it's got the ability to go a little bit faster because tension and gravity are both pointing in the same direction. Okay, it has the ability to swing a little bit faster. When it reaches the bottom of its arc, those two are opposing forces, so they're going to be acting a little bit differently. At the top of its arc, it can go just a little bit faster, and we can see that here with our velocity.